Welcome to this session on research methodology. Today, we are going to explore two of the most powerful tools in a scientist's toolkit: prediction and explanation. Whether you are studying animal behavior, ecology, or human diseases, understanding the difference between these two concepts is absolutely essential. They are the twin engines that drive the scientific method forward. Let us dive in and see how they work together to help us make sense of the universe. To begin, let us think about how we use these ideas in our everyday lives. Imagine you are standing outside and you see dark, heavy clouds gathering while the wind starts to howl. You immediately think to yourself that it is going to rain very soon. That thought is a prediction. You're guessing what will happen next based on what you see right now. However, if you were to describe how the warm moisture in the air rose, cooled down, and condensed into water droplets to form those clouds, you would be providing an explanation. We use both naturally, but in research, they are formalized superpowers. Now that we have an intuitive grasp, let us look at the formal definition of explanation in research methodology. Explanation refers to the rigorous process of identifying the underlying causes, mechanisms, or reasons why a specific phenomenon occurs. It answers the fundamental question of why something happens. It does this by connecting observed facts to established theories or logical frameworks. Essentially, explanation looks backward. It takes the data we have already collected and helps us understand the hidden reasons behind it. Without explanation, we just have a pile of facts with no connecting story. While explanation looks backward, prediction looks forward. Prediction is the scientific ability to forecast a future event, behavior, or outcome based on current data, identified patterns, or theoretical models. It answers the question of what will happen next under a given set of conditions. A robust scientific theory must successfully do both. It must explain past and present observations logically, while also generating accurate predictions that can be tested in future experiments. If a theory can explain things but cannot predict anything, it is often just a convenient story. Understanding this delicate balance is absolutely critical because it forms the backbone of the scientific method. Let us see what happens when we lack explanation. Researchers might find strange correlations that have no real meaning, such as noticing that ice cream sales and shark attacks increase at the exact same time. Without a proper explanation, one might falsely predict that eating ice cream causes shark attacks. But with proper explanation, we realize that warm summer weather is the hidden cause for both people buying ice cream and swimming in the ocean. Explanation keeps our predictions grounded in reality. Conversely, we must also understand what happens if we have explanation without prediction. Without prediction, our explanations remain completely untestable. This means we could invent any logical-sounding reason for an event without ever proving it is actually true. In real-world applications like medicine, economics, and engineering, we desperately need explanation to design new treatments or systems. But we absolutely need prediction to ensure those designs will actually work safely in the future. Prediction is the ultimate test of whether our explanation is actually correct. To truly grasp how researchers combine explanation and prediction mathematically, we can look at the simple linear regression model. This equation shows how one variable explains another. The formula is y equals beta 0 plus beta 1 times x plus epsilon. Here, y represents the dependent variable, which is the specific outcome we are trying to predict. X represents the independent variable, the factor we believe is causing the changes. Beta 0 is the intercept, representing the baseline value when the input is exactly 0. Beta 1 is the slope, telling us how much the outcome changes for every 1 unit increase in the input. Finally, epsilon represents the error term for random factors we can't explain. When beta 1 increases, our input has stronger explanatory power. Now that we understand the general linear regression equation, let us look at a specific formula for predicting student performance. Imagine a researcher wants to understand how study time affects exam scores. The formula derived from historical data is S equals 40 plus 8 times H. Conceptually, this comes from observing past students. Here, S represents the final exam score, and H represents the number of hours studied. The number 40 is our baseline score, meaning a student who studies for 0 hours is expected to get 40 points. The number 8 is our explanatory slope. If the hours studied increases, the score increases by exactly 8 points per hour, showing the exact weight of studying. With our specific formula established, let us see an example of how we use it to make a prediction. We are given that a new student plans to study for 5 hours, and we are asked to predict their final score. We choose this formula because it perfectly models the relationship between effort and grades. We start by substituting the value h equals 5 into our equation. We multiply the 5 hours by the explanatory weight of 8, which gives us 40 additional points. Adding this to the baseline of 40 gives us a final answer of 80. Physically, this means we can confidently expect this specific student to achieve an 80 on their exam, based on their effort. This same mathematical approach applies to other fields, which brings us to our next formula regarding agricultural yield. A scientist wants to explain how nitrogen fertilizer affects crop yield. The formula derived from farming data is Y equals 500 plus 25 times F. Conceptually, this models the biological response of crops to nutrients. Y represents the total crop yield in kilograms, and F represents the kilograms of fertilizer applied. The value 500 is the intercept, explaining that natural soil alone produces 500 kilograms. The value 25 is the slope. If the amount of fertilizer increases by 1 kilogram, the total yield increases by 25 kilograms, mathematically describing how soil and fertilizer work together. Now that we have our agricultural formula, let us work through an example to forecast a harvest. We are given that a farmer plans to apply 12 kilograms of fertilizer, and we need to predict the total yield. We use this specific equation because it isolates the biological growth factor. We substitute F equals 12 into the equation. Multiplying 12 by the growth factor of 25 gives us 300 additional kilograms of yield. Adding this to the baseline of 500 results in a final answer of 800. In the real world, this tells the farmer exactly what harvest to expect from their investment, proving the practical value of our explanatory model. Now that we have calculated predictions mathematically, let us visualize this relationship. On this graph, the horizontal axis represents our explanatory variable, like study hours or fertilizer, and the vertical axis represents our predicted outcome. The blue dots represent our past, historical data. The solid red line passing through them is our explanation. It is the line of best fit that mathematically describes the trend of what has already happened. The dashed red line extending beyond the data points represents our prediction. By following this line to the green star, We can forecast a future event that has not yet occurred. The explanation anchors the line, and the prediction extends it. To wrap up our session, let us review the most important ideas. Explanation and prediction are truly two sides of the same scientific coin. Explanation looks backward. It helps us understand the hidden reasons and mechanisms behind the data we have already collected. Prediction looks forward. It uses that deep understanding to accurately forecast what will happen in situations we have not yet observed. You cannot have a robust scientific theory without both. Mastering both of these concepts ensures that your research is not only theoretically sound, but also practically useful for solving real-world problems. Thank you for joining this lecture.